So moving on with the
some of the practical questions that we didn't get to look at with some of the topics that were covered. I have routing. So before that we were going through the encoding stuff, Now it's routing. Then we went through uh, the cellular wireless network. I think was one question, right? With with four or one scenario with four questions underneath it. Okay, so on routing, here is one possible one that you're bound to come across, and this one relates to the Dijkstra algorithms, which is your link state shortest path or least cost execution. So here I've come up with a really complex, well, not that complex, a nested network of how many? Of about 10 routers or 10 nodes with various interconnecting path and path cost or route cost. Okay, and the question you might get here is try to execute a Dijkstra algorithm for the a Dijkstra algorithm for the shortest path on this particular link state routing for maybe a customer that's connected to one of these uh, routers trying to send a message to maybe a different customer or different uh, device connected to another router at a different side of this nested network. In this case, it's from a customer connected to router one. Okay, and you want to find all the shortest path, possible route that the customer um, can route packets through to each of the 10 nodes that we have, or 10 routers that you have. Okay, so we want to more or less kind of like build uh, the distro shortest path that relates to a customer here trying to send a message or a packet, some kind of information to each and every router here within this nested network, and looking and basically picking out the shortest path or using the path with the least cost involved. Okay, so that's what we have over here. So execute a gesture shortest path on a link state routing for a customer or customer one, just initialize C1 connected to router one. So the assumption is customer one is probably somewhere over here connected to this router here. And you want to find all the possible shortest path routes that it can send message to each and every other node within this given nested network. Okay, so first of all, you need to build a table. Register, you have a table, obviously, where you do have your iterations and the various possible um, nodes that you might have, or you might not sequence number of nodes that you might number of possible nodes that you could have or you could use to move the packet from that customer connected to router one to every other router within the network. So I do have my table and I've listed all there. Obviously, we can't include router 1 because the customer is connected to router 1. Okay, so router 1 is going to be eliminated. And so every other router will be, or node will be, or listed. So we do have router 2, router 3, 4, 5, 6, 7, 8, 9, 10. So basically all the uh, 10 routers besides the one that the customer is connected to. And your possible nodes that you can use for the uh, transmission are all listed. I've just gone through just to save time, I've gone through to list the possible routes for each iteration that you have. So for the first iteration, which is obviously starting from 0 point, or zero iteration, which means you are on router 1. So you only have router 1. And the question is, that means you only have one node basically, in which this case it's router 1. To move the packet to R2, then you need to figure out what it will be the shortest path or the least cost to move a packet from router 1 to router 2. In this case, if you only have one node or one router to facilitate the transmission, and it happens to be router 1, then moving the packet from that router 1 to router 2, if you look at the diagram carefully, you do have an arrow pointing, which means it's moving that way, moving that direction. So the least cost for you to move a message from a customer on router 1 to router 2 would definitely be a 1 least cost. So we'll say we'll put 1 over there. So 1 is the least cost to get a packet from router 1 to router 2. What about router 3? Now keep in mind you only have one router here, which is router 1 to forward a packet. So if you want to get to 3, which is somewhere right over here, and you're only concerned with using only this router, then you obviously cannot forward a packet to router 3 because router 3 is nowhere near router 1. Okay, it's not directly connected to router 1 for you to forward a packet to. So when that happens, or in that situation, you would say it's infinite because you can directly send the message to router 3 without going through router 2. And unfortunately, we don't have router 2 listed within our first iteration. So keep that in mind. If the initial iterations is only using the first router the customer is connected to forward the message. So it's only the neighbor, the directly connected neighbors that it can have access to directly. Any other device or node, that is out of one node connection will be considered infinite. So which means uh, when it comes to 4, 4 is directly connected to 1. So that would actually have a least cost of 2. Okay. But when it comes to 5, 5 is right over here. And to get to 5 from 1, you'd have to go through 2. But unfortunately, we don't have 2 as part of our first iteration, as part of our initial iteration. So you obviously going to state that it's infinite because you'd have to go through router 2 as well before you can get to router 5. So in this case, you just type infinite over here. Okay, I hope you guys are catching on. Uh, we're only basically using only one node to facilitate our transmission. Basically meaning that you only have one single point of connectivity to every other node. And the question is it possible? And so far, if you only have one node, in this case, which is router 1, to forward a transmission, your only directly connected nodes are going to be router 2 and router 4 because they are directly connected to it. So you just did out the least cost for those ones, which is what we have for 1 and then 2 for 4. 1 for 2 and 2 for 4. Okay, but every other one, well, yeah, from this point on, let me see. So you also do have 7. If you look at it here, it's also a direct connection to 7. So actually, with router 1, you have 4, 7, and 2 as the directly connected nodes. Okay, 6 obviously far off. It's right over here. You'd have to go through a number of routers before you get to 6, either from 7 to 6 or from 2 to 3 to 6 or the other way around. So that will be infinite. But 7, since it has direct connection to 1, router 1, we'll have to use its least cost. In this case, the least cost here is 8. That's the direct connection to it. That's 8. For router 8 or node 8, which is right up here, there's no direct connections. You'd have to go through a number of routes or node devices or routers to get to 8. So at the first iteration or initial iteration, it will be infinite. So will 9 be as well as 10. Okay. Now moving on to the one iteration. So now we start from 0, which is using the device that's connected to directly, or using the device itself as the point of reference for the transmission. You have the sequence of Dijkstra of executing the Dijkstra shortest path. Now moving on to the second iteration, or more or less, yeah, the second iteration. So 0, 1. So second iteration. Now you do have 2 nodes to work with. So the uh, the options have increased. Basically, you actually have 2 other options, which in this case it's router 1 and router 2. So you do have 2 nodes to actually forward the message from customer 1. Okay, so that will actually give you much more possibilities. Now you're gonna have a bit more possibilities that are gonna be infinite anymore. Okay, so let's start with the first router, which is router 2. To forward a message directly to router 2 with 2 options, in this case router 1 and router 1 itself and router 2, you obviously still do have your 1 least cost. Okay, for 3, now you can get to 3 because then you have 1 and 2. You have router 1 and 2. And that can facilitate you to get towards 3 because router 3 is connected directly towards router 2. So in this case, it's not going to be infinite anymore. It will actually be what? The least cost associated to that route, which in this case is what? 2. Sorry, it's 1 plus 2, right? Because you have to go from 1 to 2 and 2 to 3. So there's 1 here and there's 2 here, that's 3. So the least cost will be 3 to send a message from customer 1 connected to router 1 to router 3. So where they give the assumption is made there's a customer connected to router 3. Okay, so we're just forwarding messages to customers connected to all these various routers or nodes that we have within the this nested network. Okay, so for 3, moving the packets from router 1 to router 3, the least cost will be 1 plus 2, so hence the 3. For 4, it would be the same as 2 because you do have direct connection already. Now let's go 5. 5 is now 5 is directly connected to 2, so you do have a least cost calculation of 1 plus 1, which is going to be 2. So it's no more going to be infinite now. It's going to be 2. Okay? Because, like I said, 5 is directly connected to 2 now, and 2 is part of our node for our second iteration. Okay? So you have 2 options. You have 2 nodes, possible nodes that you can forward a message to. Now, what about 6? 6 is right up here. And we only have router 1 and 2 to forward a packet to any other nodes within this network. And 6 is not directly connected to any of the 2 nodes iterations that we have. So it will be infinite. It will still be infinite. What about 8? 8 is right up here and it's way off from either 1 or 2. So that would be infinite. Oh, sorry, 7. I'm sorry, 7. 7. 7 is still directly connected to 1, so you can still get that same 8. But 8, router 8 on the other hand is way off from 1 and 2, so that would be infinite. It will still remain infinite. And I'm pretty sure that would apply to 9 and 10 as well, since they're way off from this 1 and 2 nodes that we have for our second iteration. So these two will continue to be infinite. Now we're in our third iteration. So now we do have 3 nodes to work with. 3 nodes to actually forward the message through. In this case, we have 1, 2, and 4. Now, someone might probably be asking, why did you choose 4? Well, we're looking at the closest proximity nodes first, before we move on to the ones that are a bit far away. So we started with 2, we started with 1 to 2, which are the closest one, 1 to 4, closest one, right? And then obviously when we do come down, we're even going to encounter 5 before we can even get to 3. Actually, we can incorporate 3 after 2. But anyways, we have 1, 2, and 4 now. So I'm just going by the directly connected nodes to 1 as my iteration points for the nodes that I have to work with. Okay, so now that we do have 1, 2, and 4, which is this, that, and this directly connected to 1, let's try to figure out how to move the packets from router 1 to every other node. So for 2, it will still be the 1. That 1 is still the shortest path. For 3, uh, it will be the same again. It will be 1 plus 2, which is your 3. And for 4, it would also directly be 2 because they're directly connected. So that will still be 2. Oh, sorry. Now let's look at 5. 5 will also be 2 because you still have that 1, 2 option, and 4. But you directly connected to 2 anyway, so you can just go with 1 plus 1, which is 2. So it still remains 2. Now 6. 6 is right up here. 6 has no, it's still nowhere close to uh, the 3 nodes within that third iteration that we have, which is 1, 2, and 4. 6 is still not connected directly to any of these 3 that we have. 1, 2, and 4. 1, 2, and 4. 6 is right up here. So we still can't access it directly, which will put it in, which will still make it infinite. For 7, look at it very carefully. Now that we do have 4 as part of our node options to route the message, we can try to recalculate our shortest path now. Before that, when we had only 1 and 2, within that second iteration, the only direct path was from 1 to 7, and it cost us 8 metrics. Okay? Now that we have 4 inclusive and 4 is connected to 7, we can find out whether we can get a better least cost now compared to the 8 that we had as a direct connection from 1. So if you look at it carefully, you're going to have 2, 2 plus 1, that is 3. So now it send a packet from customer 1 through router 1 or router 2 or router 4 would actually get you a much better least cost, which in this case is 3. And we got a 3 by using router 1 to router 4, which is 2, and router 4 to router 7, which is 1. So 1 plus 2 is 3. So you notice that we actually now decrease our cost now from 8 to 3. Okay, more or less because we had more options at the third iteration. So yeah, the third iteration. Okay, now what about 8? 8 is now within range of any of these 3 that we have, 1, 2, and 4. It's still not within range. So we still have an infinite reference. And so will 9 and 10. Now let's move on to our fourth iteration. Now within our fourth iteration, we do actually have 4 nodes to work with. And the nodes include 1, 2, 4, and 5. So I'm not going with 1, 2, 4, and 5. It can still be, it can either be 1, it can also be, it can also be 1, 2, 3, and 4. Okay, since we're building up more iterations or allowing for more options or more nodes to facilitate the transmission. But I just chose to go with 5 first. And I think I'm going through that approach based off just numbers. It could have been just been 3 starting out first. Okay. All right. I think I used it. I used the 5 because I had 4, and I wanted to introduce 5 as the next closest one before I put the 3 in the middle. Okay. Anyway, you can go about it in that manner, in that fashion, where you have 1, 2, 3, and 4. Okay, that should also work. Okay, so great. So now you have 4 nodes to work with, the question is what will be the least cost to move the packet from 1 to 2 again? It will still be 1. 1 is still the least cost. It's literally the least cost that you can get within this entire network that you have. Now, what about to router 2? So router 3. Router 3, let's take a look at it again. Can we find any other shortest path now that we have 4 inclusive? Now we have 5 and 4 inclusive, sorry. Really? Well, let's go through it. If we're to go through router 1 to 2 to 4, so to 5, just to get to 3, our least cost would have increased from 1 plus 1, which is 2, plus 4, it will be 6. So that's 6 on this route, which is now ideal. Well, let's try this direction and see. In this direction, we have 2 plus 3, which is 5. Now, what about from 1 to 2 and 2 to 3? It was 1 plus 2, which is 3. So obviously 3 is much more less. It's actually smaller than compared to going through this other routes, going from router 1 to 4 to get to 3, or moving from 1 to 2 to 5 to get to 3. So we'll still maintain the 3. Okay. Now what about 4? Getting to router 4. It'll still be the 2 will still be the shortest. 5. It will still be 2. Because it will still be from 1 to 2, which is 1. 2 to 5 is 1, and that's 2. What about 6? 6 is still off, it's still out of range. So it's still going to maintain the infinite. It's still out of range, you think about it, because uh, we have 4 nodes to work with right now. We have 1, 2, 4, and 5. And none of these 4 have a direct connection to 6. It is 3 that does have that direct connection, but we don't have 3 here yet. We've not included 3 yet, so we can't get to 6 directly. So that will still put 6 at the will still keep 6 at the infinite level. 7, on the other hand, will still maintain its 3, which is from 2 plus 1. That is from router 1 to 4 to 7. 8, now look at it. We had 5, right? We had 1, 2, 4, and 5. 8 is directly connected to 5. So now we're actually going to have a least cost for 8. It wouldn't be infinite anymore as it used to. Now let's try to figure out what would be the least cost to get to 8 from R1. So we still have 1. Using this direct path here, you're going to have 1 plus 1, 2, 2 plus 2, it's 4. So 8 will now have a least cost of 4 to get to it. 9, on the other hand, is still way off, so it'll still be at infinite. And same applies to 10 as well. Okay, so moving on, now we are at the fifth iteration where we do have uh, 5 nodes to work with. And now we have 1, 2, 3 is now been included, 4, and 5. So now you have 5 nodes to work with. So that will bring maybe a bit more better connectivity or least cost path to calculate or to work with. Okay, now let's see. For 2, 1 still remain because 1 still be the least cost direct connection. For 3, let's see. Since we do have now 1, 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now you do have like this range of routers to forward the messages. So now the least cost to get to 3 will still be obviously 3. Will still be 1 plus 2, which is 3. That still remains at 3. What about 4? 4 will still have the same 2 because 2 is still the shortest path. 5, on the other hand, will also carry the same least cost of 2, which is 1 plus 1. Now, watch what happened with 6. Since now 3 router 3 or node 3 is inclusive, we can actually get to 6 now because node 3 is actually directly connected to node 6 or router 6. So if it's a customer connected to that, you can actually forward the transmission to that person directly without having an infinite route allocated to it anymore. So now we just have to calculate the least cost associated to getting the packets from router 1, from the customer C1, all the way up to a C6, to a customer connected to C6, router 6. So we do have a number of options over here. If you do the math properly, to get to 6, we can go from 1 to 2 to 3 to 6, or we can go from 1 to 4 to 3 to 6. Okay, or we can go from 1 to 2 to 5, 5 to 3 to get to 6. Okay, and the question is which of those routes gives you the shortest path? Now let's go through and see which one has the shortest path. If we went through router 4 path, the cost will be 2 plus 3, which is 5, plus 2, which is 7. That's if you were to go through router 4. That's 7 to get to 6. What about if you were to go the other way, this way, where you go to router 1, router 2, router 3 to 6? Those are the math. 1 plus 2 is 3. 3 plus 2 is 5, which obviously is smaller than going through 4, which gave us 7. Okay? Now, what about if you were to go through 5? It will be 1 plus 1, which is 2, plus 4, which is 6, plus 2, which would be 8. So obviously the best route is from 1 to 2 to 3 to 6. And that was 5, right? That's 1 plus 2, 3. 3 plus 2 is 5. So to get to 6 is now 5. Getting to 7, This is still the shortest path going through 4 to remains at towards uh, 3, right? 2 plus 1. 8, on the other hand, will still have the path, this direction path, which was 1 plus 1, 2, 2 plus 2 is 4. So it'll still be 4. Can we get to 9 directly now? No, no, still not yet. We still don't have enough nodes to get to it. I think we'll start considering 9 and 10 after we include 7 and then 8. That's when we start getting closer to these other two here. So we still have infinite for these guys. And 10 will still be infinite. Okay, so I hope you guys are catching on. This is looking um pretty built up now. We kind of like having a good execution here because now we build up a lot more iterations. Okay, so move on to the sixth iteration. Now you do have 1, 2, 3, 4, 5, 7. Okay, so you do have 6 nodes at your disposal to forward the packet. Okay, so starting with router 2, it will still be 1, it will still have 1, 3 with 7 inclusive. You still have 3, you still this shortest path to get the message to it, just 1 plus 2, 3. When it comes to 4, it will still be 2. 5, it will still be this approach, which is 2. 6, with 7 inclusive, all right, with 7 inclusive, now you can go from here to 6, using only going through 2 nodes, all right. But does that give you a least cost? So let's see. If you were to go, since now you have 7, if you were to go 7 approach or 7 route, it would be 8 plus 1, which is 9, as compared to going from 1 to 2 to 3 to 6, where you're actually using up 3 nodes just to get to 6, but it actually has the least cost. So you notice, uh, so sometimes passing through a number of nodes actually has a least cost than going through only 2 nodes or going through limited nodes. Okay. So 6 will still go from R1 to R2 to R3 to R6, which is 5. Okay. So now you can tell that having the going through the minimum nodes or routers within a network just to forward packets does not guarantee you a minimum time. Sometimes going through even multiple nodes can actually guarantee you quicker time than going through limited nodes. Okay, it all boils down to the metrics, the cost associated to all those links involved. Okay. And now what about 7? 7 is still the best approach is still go through that, which is 2 plus 1, 3. 8, still this is the best route, right? which gives you a 4. 9 is still way off, even though we've included 7, it's still way off, so that's still infinity. But now let's watch 10. 10 is directly connected to 7, so now it wouldn't be infinite. We actually have a least cost now. And in this case, you can either go from R1 to R7 to get to R10, or you can go from R1 to R4 to R7 to get to R10. The question is which one of them has the least cost. If you were to go directly 7 route, direct 7 route, it will cost you 8 plus 1, which is 9. But if you were to go, if you were to go through only 2 nodes just to get to 10, it will actually cost you 9 metrics. But if we were to go through 3 nodes, which is from R1 to R4 to R7 to get to R10, the cost involved is 2 plus 1 plus 1, which is 4. Right? So now I think 10 is actually 4. Okay? Okay, moving on. So now we are the 7th iteration, and now we've included 8 as well. So now we have 1, 2, 3, 4, 5, 7, and 8. 6 is not inclusive yet because of where C is embedded. And you could as well, I mean, since you have 3, you could have just included 6 directly. But I wanted to build it up in such a way that we look at the ones that are with close connectivities. Okay? So just be mindful how you build up your node for the various iteration. Okay? But in the long run, you're obviously gonna for the chance that you're gonna end up with the same least cost values down the line in terms of when you get to the full iteration, you're gonna know that you get the least costs are gonna basically spread out evenly. Okay, so now with 8 inclusive, we can actually get to 9 now, right? So for 1, it will still, for 2, it will still be 1. For 3, it will still be 3. For 4, it will still be 2. 5 will still be 2. 6. 6, now you can get to 6 either via this route or this route, right? The question is, does this give you a cheaper route, cheaper least, a least cost, or does this option give you a least cost, or does this option give you a least cost? We can tell already that the going through 7 route is going to cost you a higher cost because of the 8 already associated with this from 1 to 7. Okay, so we can forget about that one. Let's focus on this route. Okay, so 6 will still be 5 because it's 1 plus 2 plus 2, which is 5. 7 still has got this route to work with, and that's still 3. 8 will still have this particular route, which gave us 4. Now watch 9 now. Since we've included 8, right? 8 is not part of our uh, uh, node iteration option that we have. Okay, so now we can actually get to 9 because 9 is directly connected to 8. And this is a question is that what's the cost involved? What will be the least cost involved? So the if you were to go this direction, which is the optimal direction to go through, or the optimal path to go through anyways, we have 1 plus 1, 2, 2 plus 2, 4, 4 plus 3, which is 7. Okay, so now we have 7, and 10 will still hold on to that 4. Okay, now we've included 6. So now you have the option to get to 8 either through this route, through the route, if you were to go if you wanted to go through 6. Okay. So for 2 it will still be 1, 3 will still be 3, 4 will still have 2, 5 will still have 2. If we can beat some of these values or some of these metrics cost. 6. Now what's 6? Since now we've included uh, 8, 6 and 8 in our node for the for that particular for this particular iteration. Um, the cost of getting to 8 um, would have more option, and then you have this option either to go through 1, 2, 3, 6 to 8, or 1, 2, 4. Sorry, 1, 4, 7, 6 to 8, or 1, 2, 4, 8. Right? A question: which one of these will have the least cost? We can go through them. If we were to go through this path, we would have 2 plus 1, which is 3. 3 plus 1 is 4. 4 plus 4 is 8, which is still too high. 6 will still have wait, I think when we included 8, 7 and 8, this should have changed. Because, yeah, well, let's go back to the seventh iteration when we had 7 and 8 inclusive. I think it should have decreased. It's 6 going to 6 should decrease now. Thanks to the fact that you have 7 and 8. Yes, should decrease. So it was 1 plus 1 plus 2, which is 4. 4 plus 3 is 7. And then you have uh, from 1 to 2 to 3 to 6, which is 1 plus 2, 3, 3 plus 2 is 5. It's still 5. And then what about from this direction? You have 2 plus 1 is 3, 3 plus 1 is 4. There you go. So this should have been 4. When we had 7 inclusive. Sorry, when we had uh We had 7 inclusive. It should have even been 4 over here. Because now you're going from 7 to. Yeah, it should actually decrease. So it shouldn't decrease over here. Yeah. So if you had 1, 2, 3, 4, 5, 7, which is 1, 2, 3, 4, 7. That's 5. Yeah, it should have been 4. So that's about right. So now that you include 8, 4 is still the least cost involved. Okay. All right. So coming back to what we're on earlier on. So now if you have 1, 2, 3, 4, 5, 6, 7, 8 nodes within the eighth iteration, I think you still 4 will still hold out for 6. To get to 6 is still the shortest path is from 1 to it's through 1 to 4, which is 2. 4 to 7, which is 1, 3, and then from 7 to 6, which is 1, so 4, it'll still be 4. Okay, now what about 7? Even though we included 8, 6, and all that, does the value for 7 change? Well, let's go through and see. It wasn't looking at a cost from 8. So it will still be 3. Now, what about 8 itself? It's still this route, which is the most least cost involved, which is 4, right? It's 1 plus 1, 2, 2 plus 2 is 4. For 9, 7 still holds. This will still be based off this direction as well, since you have 1 plus 1, 2, 2 plus 2, 4, 4 plus 3, still 7. What about 10? 10 will still be this direction, which is 1, which is 2 plus 1, 3, 3 plus 1, 4. Last but one iteration, you actually have 9 nodes to work with. For R2 it will still be 1, R3 will still be 3, R4 will still be 2, 5 will still be 2, 6 will still be 4, 3, 4, 7 as well, and 4. I'm just looking at the sequence before that, because the only difference that we have with this last but one iteration is by the introduction of 10, and since 10 is on this side, it's on the far side. Uh, Getting to the previous or the nodes before that will still carry their previous values. Okay. Now the last iteration where you have all the 10 nodes involved in the transmission. Once again, for 2 will still be 1. For 3 will still be 3. Yeah, and looking at, so now we've included 9. That's what's inclusive now. 9's all the way up here. And the nodes before it would obviously, you know, away from it. So there's a chance that it will carry a lot less cost. I mean, it's not um, set in stone for that because the metrics, the costs might be different. The costs are different, and and it could change uh, the least cost associated to a particular path, regardless of where it's positioned. Okay, it's just as in this case, it looks like it's going to be more. So the previous values will still remain. This will still be 2. So going to 5 will still be 2. Going to 6 will still be 4. Oh, right? So it's going to 6, 1, 2, 3, 1, 4. It'll still be 4, 6, 7, 3 still. This route is still holds. 8, same. For 9, um, it will still be this approach, right? Which was 7. So which is 1 plus 1, 2. 2 plus 2, 4. 4 plus 3, 7. And finally, 10 will still be 4, which is from this path. 2 plus 1, 3. 3 plus 1. So there you go. We have our executed shortest path uh, uh, for a linked state routing based off customer 1 connected to router 1 with the assumption of its forwarding message or packets from itself to every other node within this given nested network. Now we just have to highlight. Let's try to figure out which are uh, the routes that give us the least cost. So for router 2, the first one was the value. Okay, first value. Looking at 3, that is also its first value. 4, same. 5 out of this, the first is 2. Out of this, it was 5, 4, 4. So 4 was the least, so that should be this guy here. This, it started with 8 before it became 3. So 3 started as the lowest or the shortest. And then 9, from 8 it was, this is the usual. The usual. So these would be your um, more or less your least costs associated with moving the packets from customer connect to R1 to every other node. This is the least cost. We good? So our iteration is practically tabulation is practically all filled up nicely. We identified of our least cost, where they start from, which routes, which nodes were involved as well to give us the least cost. Okay? So that will be your execution for the Dijkstra algorithm, for the Dijkstra shortest path. This will be the tabulation of your executed Dijkstra shortest path on this particular link state routing. Okay?